A very good evening. This is Morgan, Assistant Professor, Department of Agricultural Engineering, Sri Shanmugha College of Engineering and Technology. Today I'm going to discuss about open channel. Already in the last class we discussed about open channel flow with a free surface exposed to atmospheric pressure. In case of pipe flow, full pipe flow under hydraulic pressure. So already we have discussed about the discharge through open channel by these four equations. One is about chassis constant, another one is about Mannings, and the third one is basins, and fourth one is Coulter. Discharge through open channel by chassis. The diagram it can able to show a uniform flow in open channel with have two sections, section 1-1 and section 2-2. Section 1-1 in the upstream side, section 2-2 in the downstream side. So the water flows from section 1-1 to section 2-2. So in the section 1-1 and section 2-2, the forces acting on the water, one is about the weight of water which is flowing from section 1 to 2, and the other one was about frictional resistance with respect to the slope of channel over the flow. The weight of water is W sin I towards the flow. Friction resistance is F P L V square. F is friction resistance, P is pressure, force, L length, V velocity. So where W is equal to weight density, that is density, weight of fluid. Weight of fluid is equal density into volume. Weight density is W, volume is area of the channel into length, so WAL, equating these two forces, W sin I, W can be replaced by WAL into sin I is equal to FPLV square. When equating these two forces, we may get the formula where V is equal to C into square root of MI. So where C is nothing but square root of W by F, where M is A by P sin I. A by P is equal to hydraulic radius, where W by F, that is chassis constant. So we have the formula where velocity V is equal to C into square root of Mi. We are equating the equations number 2 and number 3 in equation number 1, where V is equal to C into square root of M into sin I. For the values of I will be very small. So where sin I, that is tan I, is equal to I. So the equations will become where the velocity of flow, where V is equal to C into square root of Mi. The velocity of steady uniform flow, that means uniform flow open channel, is given by chassis, where V is equal to C into square root of Mi. M is hydraulic mean depth A by P, A is area, P is perimeter, I is bed slope, that is HF by L, where C is chassis formula is square root of AG by F. The dimensionless terms, means dimension formula for chassis is L power 1 by 2, T power minus 1. To find the chassis coefficient, the following empirical formula are used. The one is Manning, the second one is Coulter, and third one is Basin. And the relationship between chassis C and Manning's N is where C is equal to M to the power 1 by 6 by N, where M is Manning's hydraulic mean depth, N is Manning's constant. And for Coulter, where C is equal to 23 plus 1 by N plus 0.00155 by S0 whole divided by 1 plus 23 plus 0.00155 by S0 into N by square root of R, where N is Manning's, R is mean hydraulic divided as A by P. Next is the relation between basin and chassis. C is equal to 87 plus 1 by MIR. M is coefficient of basin, depends upon the surface roughness. Next is about the conveyance factor, where V is equal to C into square root of Mi. So where EQ is equal to area into velocity, substitute the value of V, so AC into square root of Mi. We are splitting the a square root term, where A into C into square root of M into square root of I, where AC square root of M is conveyance, where K is equal to AC into square root of M is a conveyance factor for open channel. and the unit for the K is meter cube per second. And based on this discharge equations, we have the formula, means we have the problem. Find the rate of flow and conveyance for a rectangular channel 7.5 meter wide for a uniform flow at a depth of 2.25 meter. The bed slope of the channel is 1 in 1000 and chassis constant is 55. Also determine the type of flow. According to the flow number, we should categorize which type of flow, either it is subcritical, critical or supercritical. Here the data which is given for the rectangular channel is width of the channel is given, depth of the channel is given, bed slope of the channel, and chassis constant is 55. So B is 7.5 and D is 2.25, where I is equal to 1 by 1000, where C is equal to 55. So area for rectangular is BD, so breadth into depth. For perimeter is B plus 2D. We are making the ratios A by P is M. So we have the discharge formula with respect to chassis, where Q is equal to AC into square root of Mi. Substitute the value of AC M into I. We may get the value of Q is equal to 34.86 meter cube per second. The second unknown is about conveyance. So conveyance, where K is equal to A into C into square root of M. So substitute all this value, we may get the value of K is equal to 1102.41 meter cube per second. The third one is about the type of flow. According to the fluid number, Fr is equal to V divided by square root of G D. V is velocity, G is acceleration due to gravity, D is depth of channel or flow. The value is about less than 0.1. If the value is less than 0.1, so the flow is said to be subcritical. The second is about the trapezoidal, same conditions. We just calculate the area of trapezoidal, perimeter of trapezoidal. From this we can able to calculate the value of M. Here with respect to chassis, the discharge equations, Q is equal to AC into square root of Mi, where shear stress that has to calculate, where shear stress is equal to Mi, omega into Mi. So that is GMI. So 9.81 into M value is 1.62 into I is 1 by 4000. So you can get the value of 3.97. Next is about the energy equation. Here, as in the case of chassis equations, we have two sections, section 1 and 2. Section 1 is in the upstream, section 2 is in the downstream, and we have a bed slope with an angle of theta. And section 1 there is a height of z1 plus y1 cos theta plus alpha v1 square by 2g, and for the section 2 z plus y2 plus alpha v2 square by 2g. The figure shows a steady varied flow in the channel. The total energy head at any point at a depth d below the water surface is H is equal to Za plus d cos theta plus alpha v square by 2g. Here the total energy will be constant for all the values of d from 0 to y at normal section through point A. The total energy at any section whose bed is constant at an elevation Z above the datum, where H is equal to Z plus y cos theta plus alpha v square by 2g. So the head is for the two different sections. For 1 H1 is equal to Z1 plus y1 cos theta plus alpha 1 v1 square by 2g. The total energy at the section 2 H2 is equal to Z2 plus y2 cos theta plus alpha 2 v2 square by 2g. So in case of the slope of the channel is very small, so let we have the theta is 1, so where cos 0 is equal to 1, so theta will become 0. So where H is equal to Z plus y plus alpha v square by 2g. The specific energy, the total energy of the channel flow with respect to datum is given by Z plus y cos theta plus alpha v square by 2g. Here cos r theta is equal to 1, where alpha is equal to 1. So in case of alpha, that is called as energy correction factor unless otherwise specified. We just make the value of alpha is equal to 1 as in the case of open channel. So if the datum coincide with the channel bed, there is no bed slopes, the theta becomes 0. It is known as specific energy. It is denoted by the symbol E, where E is equal to y plus v square by 2g. This is the condition for critical depth. We have the formula for E is equal to y plus v square by 2g, where in case of discharge, where Q is equal to area into velocity, as in terms of V is equal to Q by A, let again substitute the value of Q square by 2ga square. The variations of E with respect to y is represented by a cubic parabola shown in figure. It is seen that There are two positive roots we can get for the equations of E, which indicates that for any parabolic curves, the Q can be passed the given channel at a depth for the same specific energy. So the conditions for specific energy E1, smaller depth, larger velocity, that is Y1, larger depth, smaller velocity, the value is Y1 dash. These two possible depth having the same specific energy is known as alternate depth. For a given Q, the specific energy is increased. The difference between the two alternate depth increases. On the other hand, when the specific energy is decreased, difference between the two depth, that is Y1 dash minus Y1, will decrease. At certain value, the specific energy will become a minimum specific energy. The depth will merge together. So at this point, there is no difference between the value. That condition is known as minimum specific condition, and the condition is called as minimum specific energy conditions. The condition of minimum specific energy is known as critical flow condition, and the corresponding depth YC is known as critical depth. At critical depth, the specific energy is very minimum. So we may get the specific energy equations. We are differentiating these equations with respect to y. We may get the conditions alpha q square Tc by GAC is equal to 1. We are correlating with this. We may get the equations is equal to q square by G is equal to AC cube by 2. With respect to the condition for critical and specific energy, let me calculate the specific energy and critical depth and Froude number value for the rectangular section. The condition for critical depth is q square Tc by Ga cube is equal to 1. When multiplying by 2 on both sides, let we have these equations. V square by 2G is equal to 1 by 2 times of Yc, where Vc square by 2G, we are replacing in this energy equations Yc plus half Yc. So that is a 3 by 2 times of Yc. That is the value of critical energy. Same for critical depth, where Yc is equal to q square by G, the whole power 1 by 3. As in the case of Froude number, A by T is equal to Y. So the F will become V by square root of G Y. So this is all about the specific energy, condition for specific energy. With respect to the condition for specific energy, how to calculate the minimum critical energy as well as critical depth and Froude number for rectangular sections. Thank you. The remaining discuss on some other class.